Since the dawn of civilization, humans have been constantly pushing the limits of science forward. But despite our insatiable thirst for knowledge, there are mysteries that still baffle even the brightest of minds. From the origin of the universe to the perplexing nature of consciousness itself, science is abundant with profound puzzles. This is Unveiled, and today we're taking a closer look at 10 massive questions that science still can't answer.
Do you need the big questions answered? Are you constantly curious? Then why not subscribe to Unveiled for more clips like this one and ring the bell for more thought-provoking content.
Number 1. What is the universe's origin? A great deal of effort has been put into answering our first big question, resulting in a wide choice of scientific explanations and suggestions to choose from. But still, many feel that we may never know with absolute certainty. The most widely accepted answer is, of course, the Big Bang Theory, which claims that the universe began 13.8 billion years ago, when it burst forth from an extremely hot singularity. A singularity is an infinitely small point of infinite density, which, so the theory says, contained the entire matter of the universe before it all rushed outwards. Singularities don't exactly represent anything physical, though, and are instead a mathematical phenomenon. That means that inside them, we know that physics breaks down. Nevertheless, the Big Bang Theory says that that is where we came from, and that in the first second of the universe, this point of infinite density exploded, and the cosmos underwent a period of exponential growth called inflation. Initially, it all happened at beyond the speed of light, before the rush of immense energy eventually cooled. Once temperatures dropped, atoms and particles managed to form, later forming stars, galaxies, and the entire structure of what we now know as the universe. While it's a widely accepted theory, it does leave some questions unanswered, and so a great deal of alternatives exist. One example is broadly known as cosmic inflation, an idea that would be viewed as an extension of the Big Bang. It explains the expansion of the universe in greater detail and matches up with observational evidence, but it doesn't really address exactly what started it, what drives it, or how it will end. More radical alternatives include string gas cosmology, which proposes that the universe began as a box of quantum strings, the tiniest states of matter possible, in thermal equilibrium. If the box of strings were true, it would bypass all the problems that a singularity throws up. But the problem is that string theory in general is currently unproven. Number 2. What is the fate of the universe? Moving to the other end of the timeline, how the universe will end is perhaps even more difficult to know. Currently, our universe is observed to be expanding at an accelerated rate, and we believe this to be happening due to dark energy, which makes up roughly 70% of the cosmos. But unfortunately, that's pretty much all we know about this mysterious force. Even so, the result is that everything in the universe, from planets to stars to galaxies, is getting further and further apart. Eventually, in one version of events at least, the stars will exhaust their nuclear fuel and the cosmos will fade into darkness. Even black holes will evaporate due to Hawking radiation, leaving a dark cosmos behind, in a bleak scenario called heat death. But actually, there are other theories as to the universe's fate as well. Since we don't understand the nature of dark energy, things could indeed go differently. The Big Crunch theory wonders if universal acceleration could instead reverse someday, causing the entire cosmos to gravitationally collapse. The end result here would be everything we know spiraling back down into an extremely dense hot state, into a new singularity. It could end there, or it could potentially lead to another Big Bang. This more cyclic model gives our universe a poetic end and new beginning, with the cosmos infinitely repeating itself for eternity. It's often referred to as the Big Bounce. Finally, though, the Big Rip theory presents a different and more horrifying story. It predicts that the ever-unknowable dark energy will actually grow stronger over time and will eventually overcome all other forces. In this frankly catastrophic scenario, the increased dark energy will tear apart galaxies, stars, planets, and the entire fabric of space-time. Overall, the heat death scenario we started with is the most favored among contemporary scientists, but it's also certainly unclear precisely how dark energy might evolve in the future, so nothing is truly off the table. Number 3. What are dark matter and dark energy? So we don't understand 70% of nature. What about the other 30%? Well, the sober reality is that only 5% of that is regular observable matter. The other 25% is dark matter. So what are both dark matter and dark energy? Despite making up approximately 95% of the universe, we have little to no idea as to their nature. Combined, they could reasonably be labeled as the most intriguing and mysterious components of the universe. Dark matter is unlike ordinary matter because it doesn't emit, absorb, or reflect any light. As such, it is completely invisible to light. We only know it exists thanks to the indirect gravitational effects that it has on cosmological objects, such as galaxies. We can view them from afar, observe how they behave, and we know that there must be a massive amount of mysterious unseen mass that's orchestrating what we see. That mass is dark matter. We also have the phenomenon of gravitational lensing. This is a peculiar effect that occurs when light from distant objects is bent by massive, often invisible matter. Again, in many cases, it's dark matter that's to blame. Dark energy, the more dominant of the two, is arguably even more mysterious. We chiefly discovered it via observations of supernovae, which first revealed the universe's expansion. The most widely accepted suggested explanation is that dark energy is a hidden, repulsive force that's forever working to counteract gravity on the grandest of scales. We can find evidence of it via the energy density of space as well. As the universe grows, matter dilutes, but the energy density remains constant. The answer? Dark energy. The reason? We just don't know. Number 4. Why is there a matter-antimatter imbalance? As it turns out, regular matter is also pretty perplexing. Specifically, it's uncertain why matter dominates over antimatter in our universe. According to the standard model, there should be an equal amount of matter and antimatter in existence, but in reality, this isn't the case. So why is there an imbalance between the two? It's one of the greatest challenges in physics, and it's known as the matter asymmetry problem. To scale it back, antimatter is composed of antiparticles, which are the counterparts to ordinary matter particles, such as electrons and protons. For every one of these, there is a corresponding antiparticle with the same mass but opposite electric charge. For instance, an electron's antimatter counterpart is the positron. When a particle and its corresponding antiparticle meet, they annihilate, leaving behind gamma-ray energy. This much we know, but finding antimatter in significant quantities is a rare occurrence, and that's a little strange. If the standard model is correct, the Big Bang should have produced equal types of matter. The result would have been a universe filled entirely with radiation only. No complex structures would form, such as galaxies, stars, planets, and life. Thankfully, this isn't the case. Matter won out, and we're here to tell the tale. But discovering why that is crucial to our understanding of the cosmos. One possible explanation lies in what's known as charge parity, or CP violation. Violation is the key word here, as experiments have shown that some weak nuclear interactions violate the symmetry that theoretically should exist between matter and antimatter. It's argued that an early series of CP-violating processes in the universe are what led to a tiny imbalance, which eventually snowballed into the matter-dominated cosmos we have today. Another theory is baryogenesis, which proposes mechanisms where baryons, particles of regular matter like protons and neutrons, came to dominate antibaryons. The exact details are largely unknown, and there are several different models for this. But again, researchers believe that it could explain the fundamental issue with the matter-antimatter split. Nobody knows for sure, though, and it's a puzzle that looks set to continue long into the future. Number 5. Is time travel possible? Of course, time travel has long fascinated humanity, inspiring countless science fiction stories in particular over the last century or so. But is it, will it ever be, really possible? The first and most often retorted answer is that actually we all travel in time every day, at a menial rate of 1 second per second. But that's not exactly satisfying. What we're really asking is, can that rate be altered? Could we ever travel to anywhere that's not just incrementally into the future at the standard speed? Albert Einstein's general relativity does provide some options. According to the theory, massive objects cause a curvature in space-time, which we perceive as gravity. This curvature affects the flow of time, though, which is a phenomenon called time dilation. Among many other things, it means that astronauts aboard the International Space Station already experience time as ever so slightly slower compared to people on Earth, due to the shifts in gravity and velocity on the ISS. It all amounts to a scientifically proven manner of moving into the future at a different rate, otherwise known as time traveling. It's extremely limited, though. It requires difficult conditions, and you're still only ever going forward, not backwards. For many, it could never translate into true time travel as science fiction depicts it. If we were trying to strongman our way to a more impressive result, we have wormholes, which relativity does again allow for. These are hypothetical tunnels through space-time that, if traversable, could enable time travel reasonably easily. Unfortunately, however, there is zero evidence of wormholes in reality. And even if we had observed them, then it's predicted that they'd be extremely difficult to stabilize and perhaps impossible to ever travel through. As things stand, then, time travel is a complete impossibility. And it's a logical nightmare to boot, with variously infamous paradoxes, such as the grandfather paradox, ready and waiting to entangle anyone that ever did manage to achieve it. Number 6. What is consciousness? One of the most elusive phenomenon ever observed is consciousness. We all experience it, but what exactly is it? It's an age-old question. It's generally described as the state of being aware of and able to comprehend our existence, thoughts, and surroundings. It's central to the human experience, turning us into sentient beings, capable of introspection, imagination, and intricate decision-making. It lets us perceive the world, form memories of it, and maintain a continuous personal identity. Take it away and we wouldn't be human. Neuroscientists study the brain, determined to understand how neural processes create subjective experiences. And there are certain specific brain structures that are believed to be linked to conscious awareness. Examples are the prefrontal cortex, thalamus, and posterior cortex, which are all thought to play a crucial role in generating sentient experiences. Our neuroimaging techniques are only getting more advanced, allowing scientists to observe brain activity in real time better than ever. And as this allows them to correlate specific brain patterns with conscious states, you might imagine that the case was closed. But it isn't. There's global workspace theory, for example, which claims that our brains function more like a global workspace. According to GWT, the brain contains multiple specialized processes operating unconsciously and independently. They all handle various tasks like perception, memory, motor control, etc. But when information from these needs to be made available for cognitive functions, it enters the global workspace, which is something akin to a theater, and it's only on this stage that the conscious mind is formed. Meanwhile, on the other side of the coin, there are theories that describe consciousness as something else entirely, as something that's not tied to or generated by any one person's physical brain at all. Models such as biocentrism claim that consciousness could instead be something like a universal energy, and that our brains and bodies only ever act as temporary hosts for it. There are huge implications for life after death here, but for now it goes to show just how tricky the problem of consciousness still is. Number 7. Does the soul exist? Now we're also drawing upon the fields of philosophy and religion as well as science. The concept of a soul is that it's the non-material essence that defines our personalities and consciousness. In most tellings, it's usually immortal and separate from our physical bodies. The existence of a soul is a key aspect to most major religions. In Christianity, it survives after death, where it enters the afterlife and is judged by God. In Hinduism and Buddhism, the soul undergoes a cycle of rebirth, entering a new life form post-death via reincarnation. Philosophically, the soul is an idea that's been explored for thousands of years. The Greek philosopher Plato, for instance, also believed it to be immortal, and that it existed before inhabiting a physical body. The 17th century's René Descartes, on the other hand, thought the soul resided in the pineal gland, a tiny organ in our brains. Meanwhile, in Japanese legend, the soul is contained in the shirikodama, which is a jewel hidden in our rear ends. So all across human history, wildly different concepts of the soul have been conceived. From a scientific perspective, the soul's existence is entirely unproven and completely beyond the scope of rigorous investigation. Again, neuroscience has made some great strides in understanding how our brains potentially create consciousness. And perhaps these advancements suggest what we consider to be the soul is actually entirely created by physical processes in the brain. There isn't a great deal of difference between the soul and general consciousness here, though, so science might be said to miss the mark. In fact, for some, the soul might forever be unprovable. Number 8. How did life begin? Around 4.5 billion years ago, Earth was only just beginning to take shape. It was a hostile environment, dominated by scorching volcanic activity, a toxic atmosphere, and frequently devastating meteorite impacts. Despite this, it clearly had the essential ingredients needed for life: water, organic molecules, and energy from sunlight. Many scientists believe that life formed here, in what's often termed to be a primordial soup. They think the simple organic compounds that existed at the start gradually evolved, getting more and more complicated, until eventually they spawned life as we know it. The Miller-Urey experiment was an attempt to verify this. Carried out in 1952, it simulated the conditions thought to be present in prebiotic Earth, and it worked. The experiment demonstrated that organic molecules like amino acids can form from simple inorganic compounds under such conditions. Amino acids are the building blocks of proteins, making them a vital foundation for life. So the early 50s test could be said to have cracked the mystery. There is still work to be done, however, and there are still competing theories as to how the very first life-enabling substances arrived on our planet. There's always a little further back that we could go, and this is where science is today. One famous line of research takes us to the theory of panspermia, an increasing focus of astrobiology. Panspermia is the idea that life was initially delivered to Earth from outer space, carried here by a meteorite, comet, or asteroid. Studies of matter from space have found organic compounds such as amino acids to be present. This at least shows that the components for life are seemingly widespread across the cosmos. As to whether or not we really did begin off Earth rather than on it, it remains an open question, and the race is on to reach an answer. Number 9. Are we alone? Panspermia takes us neatly to our penultimate problem, the potential for alien life. For one, there's directed panspermia, which is a more controversial offshoot of the theory, suggesting that not only did the base materials for life come from space, but they were also purposely sent here by intelligent beings. The jury's definitely still out on that one. But aliens in general are today far from controversial. We know that the solar system hasn't been around long compared to the rest of the universe. It's only 4.5 billion years old, while the universe is at least 13.8 billion. We also know that there are billions of systems in the Milky Way with stars that are similar to our own, with a lot of these probably having planets that are very much like Earth. A lot of those planets could, even should, then be billions of years older than ours. So statistically speaking, intelligent life should be extremely common in the universe. Not only this, but Earth should probably have already been visited by aliens at least once. And yet all observations tell us this isn't the case. It's a famous quandary and discrepancy known as the Fermi paradox. So what's going on? Have we just not observed enough of the universe? Perhaps, but it seems unlikely. The Kepler Space Telescope alone has identified thousands of exoplanets, many with conditions similar to Earth. But so far, none of these have shown obvious detectable signs of life. More broadly, the Search for Extraterrestrial Life, or SETI, is an organization founded primarily to detect alien signals, but no definitive signals have ever been detected. To coin another common term for scientists working in the field, we are in the midst of a great silence. One possible answer to the Fermi paradox is the great filter. In short, this suggests that intelligent life always faces one obstacle so difficult that no or extremely few species can evolve past it. Maybe that's why there are no aliens to be found, because they've all been killed off by whatever the filter is. The somewhat frightening implication, though, is that humanity should also pass through the same filter. And currently, it's unclear if we've already done so. It's unknown whether the Great Filter is in front of us or behind us. Both options are rather bleak scenarios. If it's in front of us, then we might not be around for much longer. If it's behind us, then we likely are alone in the universe. For now, though, there's just no way to confirm one or the other. Number 10. Is there a God? Almost everyone on Earth holds at least an idea of what a god or the god is. Whether or not you believe, God is something that has seemingly spread through and shaped human history. For billions around the world, belief in a higher power is core to their faith. Most religions offer diverse perspectives on the nature of God, but more often than not, gods are omnipotent and omniscient. Many are benevolent, and a select few are pitched as being the creator of all things. Sacred texts and the testimony of prophets are cited as evidence for them, but of course, science needs a little more. Science, by its nature, doesn't address the supernatural. At its heart, it relies on empirical evidence and testable theories. It therefore doesn't have the tools to prove or disprove the existence of God. That said, science isn't inherently inescapably atheist either, as many may believe. For example, Einstein expressed a sense of wonder at the cosmos, which he called a cosmic religious feeling. Carl Sagan famously spoke of a complex appreciation for some aspects of Hinduism. On the other hand, some religious individuals believe science to be a way to explain and appreciate God's work. So there isn't always such a huge divide. In the words of the pioneering quantum physicist Max Planck, quote, "Science cannot solve the ultimate mystery of nature because we ourselves are part of the mystery that we are trying to solve." Somewhat appropriately, Planck's sentiments are open for interpretation. But with regards to God specifically, science can't answer to any particular aspect. It can only continue to unpick the mysteries of our world and reality as we live it here and now.
What do you think? Is there anything we missed? Let us know in the comments. Check out these other clips from Unveiled, and make sure you subscribe and ring the bell for our latest content.